In weak acids 2, I'm going to discuss a couple things. First off, we're going to start with a percent ionization question, which a lot of us have been struggling with. So, percent ionization is nothing more than using Rice diagrams to figure out what percent you calculated, and that's just the same as you'd find any percent you would find. So let's start off with an example. So let's say we have a 0.50 molar solution of weak acid of HA, where A is just your conjugate base. So you know that because H is H+. So let's say in a 0.50 molar HA solution, we know is 2.0% ionized. What is the Ka and pH of the solution? So we know that 2% or 2/100ths is ionized. So 2.0 out of 100, that's our percentage, is ionized of that 0.50 molar solution. So what we can calculate that, what is the total that's ionized is 0.010 moles is ionized. This is actually a very simple Rice diagram because we're given what our value is at equilibrium. So we have our HA, our acid dissociation equation. And we talked about that last time. We know my initial HA is 0.05. We assume my initial H plus and A minus is 0. And we'll talk about that later in buffers when it's not. This is going to decrease. That's going to increase by X. And we know that at equilibrium, 0.001 moles per liter is ionized. We know X is equal to 0.010 molar, which we calculated right up here. So I can calculate my equilibrium concentrations fairly easy. I have 0.9, I have 0.01, 0.01, and I can just easily calculate my Ka. I know that my Ka is equal to my concentration of H plus hydronium ions times A minus, your conjugate base ions, over HA. A can be something like acetate or fluoride, any of your conjugate bases that's actually a weak base. Moving on, I can calculate that 0.01 times 0.01 all over 0.49. And that, what we can get for values, 2.0 times 10 to the negative fourth. If we want to calculate the pH, easily, all we have to do is know our hydrogen ion concentration at equilibrium, which is up here, and that is equal to the negative log of 0.01. We get a fairly easy question here, and that's going to be the pH of 2. Again, let's just say you also want to know what is the percent ionization in a 0.20 molar HA solution. So, same thing again. We have our Rice diagram, fill in our reaction, I've been given that I have a 0.20 molar solution. Again, assume you don't start with any hydrogen ions or A minus ions, conjugate base ions. Subtract X plus X plus X, 0.20 minus X, X. If you guys want to try to solve this, that's fine. What we can get here is we can use our Ka expression from up here again. Ka is equal to concentration of H plus times concentration of A minus all over concentration of HA at equilibrium. And we know this value we calculated in the last problem is 2.0 times 10 to the negative fourth. just plug in your values at equilibrium. You have Ka is x times x over 0.20 minus x. And that's equal to 2.0 times 10 to the negative fourth. And what we get for x is a value of, you can use your solver or graph it or however you like to solve it. You can actually use a quadratic equation if you so desire. That's good practice for that, but if you don't have time for that, you can just use your calculator and get 0.62 molar. So that's what's ionized. So that's our x. That's how much ionized right here. And we know we started with 0.20 molar ionized, so we can just easily calculate our percent ionized is equal to 0.0062 moles per liter, that's the amount of ions, over a total 0.20 molar. Multiply that by 100% and we get 3.1% ionization. So let's move on to the next in a second. So let's move on here. We'll talk about some diprotic and triprotic acids. So say, for example, H2CO3, that is a diprotic acid, meaning 2 protons, 2 H pluses. So that's a little different. H2CO3, what that does when it's aqueous, it breaks down into H plus aqueous plus HCO3 minus aqueous. So the Ka for this reaction is, and I'll give you a value for it, Ka for this is equal to 4.2 times 10 to the negative 7. And the Ka expression is equal to concentration of H plus times concentration of HCO3 minus, all over concentration of H2CO3. Now, if you guys notice that this product here also has an H plus. So we can also talk about that breaking down as well, dissociating, better word. HCO3 minus dissociates to H plus aqueous plus CO3 negative 2 aqueous. So our Ka for this value is equal to 4.8 times 10 to the negative 11. So a weaker acid for the second one. Now, how do you know which one to use? They gave it a name. The first one is Ka1. The second dissociation is Ka2. So what we get for a value of this is the Ka2 up here, or Ka1 up here is this value. Ka2 is equal to the concentration of H plus times concentration of CO3 negative 2, all over concentration of HCO3 negative. So triprotics also similar. So something like H3PO4, you know, our Ka1 is equal to our first dissociation equation. So this breaks down into H plus H2PO4 negative. So our Ka for this is H plus times H2PO4 negative, all over concentration of H3PO4. Our Ka2 is going to be equal to our second proton leaving, and that is H2PO4 negative 2, dissociating to form H plus HPO4 negative 2. So we get our Ka value here, H plus times HPO4 negative 2 over H2PO4 minus. And this one even has a third one. So for our third dissociation, we have HPO4 negative 2, getting rid of its H plus, making H plus PO4 negative 3. And we have our Ka3 for this value is equal to concentration of H plus times concentration of phosphate, all over concentration of HPO4 negative 2. So we'll probably talk a little bit more about this when we talk about buffers. And now let's move on to a new topic, and we are going to talk about weak bases. And this is it for this lecture. So, for example, a weak base is NH3, ammonia, like we used in our last lab. And let's recall what a Bronsted base is. Is a proton acceptor. So, how can we explain that this is a weak electrolyte? Well, NH3, aqueous, is a weak electrolyte, meaning it will conduct electricity in solution. And how we explain that is, well, NH3, we talked about this a while ago when we talked about acids and bases. When it reacts with water, we form NH4 plus aqueous plus OH minus aqueous. Sometimes you'll see that in the form of NH4OH aqueous. This is the net ionic equation here. So what they call the equilibrium constant for this, and we have an equilibrium there, so we have ions present. And we can just write an equilibrium constant just like every other reaction. That's going to be equal to the concentration of ammonium times concentration of hydroxide all over the concentration of NH3. We're not going to include the water liquid because that is a pure substance. So we have this equilibrium constant. It's called Kb when you talk about the dissociation or with water for a base. So the Kb for NH3 is equal to 1.8 times 10 to the negative 5. So how we can apply this is, say we want to know what is the pH of 0.40 molar ammonia, NH3. And what I need to do this is I need to know my equilibrium concentration of hydroxide to figure out my pOH, which, as we remember, we can calculate my pOH from that. So, use my Rice diagram and my reaction given above, NH3 aqueous plus H2O liquid. Make sure you pay attention to those phases. NH4 plus aqueous plus hydroxide ions aqueous. So my initial concentration for ammonia is 0.4. I'm not going to worry about water since it's that pure substance. And let's say I have nothing present in solutions to start with. I'm going to decrease by x, increase by x, increase by x, those stoichiometric coefficients. And I get my equilibrium concentrations. So I use my Kb expression up here, and I can calculate my value, 1.8 times 10 to the negative 5th is equal to x times x all over 0.40 minus x. So I can solve this equation. Again, this is a quadratic, and you can solve it using the quadratic equation, or you can just use your calculator, solve that, and we can get a value of, if you want to do that now. If you want to pause and do that. But here, we'll calculate it quick, and we get 0.027 is our molarity. So our concentration of hydroxide ions is equal to 0.0027 molar. And if I take the negative log of that, my pOH is the negative log of that, which is equal to 0.0027. And I get a value of 2.57. My pOH. My pH is going to be 14 minus my pOH, which is equal to 11.43. So clearly basic. But as similar to as we talked about weak acids, it's not as high a pH as a 0.400 molar strong base NaOH. Similar to strong acids, strong bases are considered to completely ionize in solution. And we have our pH, our pOH of this is equal to the negative log 0.400, which is equal to 0.398, giving me a pH of equal to 13.6. So a couple degrees of magnitude higher. Remember, pH is a logarithmic scale than our than our weak base of the same concentration. So we'll talk more about this later when we talk about buffers and do more worksheets.